When we talk about electricity, what is electricity? It's a little bit complicated. It depends on who you ask because it's a branch of physics. You know, it's a form of energy. But we'll get into some of the basics of what electricity is. They talk a little bit about safety here. These are things that you probably already know. Something to note here is that when you talk about the circuit breakers in your home, they're called protected devices, but they don't protect you because a smallest circuit breaker you'll probably run across is a 10 amp, and usually you'll be harder to find something smaller than 15 amps, but it takes less than 1 amp to kill you. So this is what this is showing here. Even around a tenth of an amp is enough to stop your heart. They talk a little bit about fire extinguishers, use the right extinguisher. So I don't go into a lot about safety here because you're going to have it in a lot of other courses. And if you're already working, you know what the kind of dangers are in your particular environment. And when you go into a new environment, they make a point to train you on that. And it's like a paramount thing. They're concerned about your safety. They're concerned about their insurance rates. So you will get very detailed and specific safety on the job. PPE, personal protective equipment, hard hats, safety glasses, things like that. Lockout, tag out. The way this works is you've got this box where your disconnects are. And if you're going to go work on a piece of equipment, you don't want it to be energized. You don't want somebody coming and energizing it, even though you turn the breaker off so that it would be safe to work on. Doesn't mean somebody's not going to come around behind you and flip it back on. So what happens is that you turn it off, you close the box, and you put a lock, either a lock, or if more than one person is going to be working on that equipment, you put one of these hasps on it so that everybody puts their lock on it, and this can never be turned on until everybody has taken their lock off out. So lock out, tag out, put a tag, here's the lock, there's the tag. Different materials present different hazards. Some of the instruments that you use in electricity. So electricity, the thing about electricity is you can't see it. Sometimes you can see the effects of it, but when you have mechanical problems, a lot of times you see broken springs and leaking hydraulic lines and things like that. But when electrical problems occur, you don't really see them, although you can see the effects. So we need a lot of tools to measure in order for us to detect the presence and levels of electricity. Just kind of on a side, when you talk about electrical failures or faults, almost all the time, they're either an open circuit or a short circuit. If something's not working, it's controlled by a PLC. It's likely the reason it's not working is not because the software in the PLC got changed. It's likely that somebody hit a limit switch or a piece of conduit with a fork truck or something like that that caused your problem. So kind of look for obvious things before you really start digging deep for a problem. So you got a multimeter here, and you've got a voltage tester. Sometimes that's called a wiggy. Oscilloscope, sometimes you have to see. You can't just measure the electricity to see that it's there. You need to actually look at what that electricity looks like to make sure that it's not contaminated by other noise, things like that. Clamp on amp meter so that you can check current without actually opening a circuit up. Especially now, the way we're having to do these courses, stop me at any time and say, what the hell are you talking about, Dave? We got to try to maximize the way that we're doing this, and that's going to involve you guys playing an active role. So don't feel intimidated or reluctant to stop me and ask me for a different type of explanation or any question you might have. Again, you can download these PowerPoints. You can look at the PowerPoints in the viewer, but the animation, this won't work. But if you download them, you can play the show just like what we're doing right now. So this is showing how to use a meter in a multimeter being used as a voltmeter, being used as an amp meter, and being used as an ohm meter, and apparently testing a diode. Fasteners, and this is about using the right tool for the right job. How many of you have used a screwdriver to pry something with?
Yep.
Yeah, it's not supposed to do that, but I've done that. How many of you used it as a chisel? A screwdriver is a chisel. How many of you used vice grips as a hammer, chiseling with a screwdriver? I mean, it works, and there's been a lot of times I've been under a car that I was like, I know I should get a Phillips head screwdriver, but I think if I put this flat tip in at an angle, I can get this thing to move, so I don't want to crawl out from under here. Yeah, I mean, so we all have done that, but obviously it's easier if you have the right tool for the right job, but also there's that safety thing. If you're chiseling, with chiseling a screwdriver with vice grips, pieces of the handle can come off and put your eye out, just like what your mom warned you about. So use the right tool for the right job. Has anybody seen one of these posit drive heads on something? So these are some electrical fails. All right, let's talk about chemistry a little bit. So everything's made out of atoms. You probably learned that one already. And the parts of the atom are important to us because of the electron part, this piece that's floating around, going around the outside. That is what makes up electrical current. Electrical current that flows through the wires to all your appliances, flows through the filaments of the light bulbs, is atoms. Just like water flowing in a pipe, electrons, these pieces of atoms flowing in a conductor, is what electric current is. Current, just like a current of water. So it's a flow. All atoms have a different number of electrons that are going around them. A point to note here is that the electrons have a negative charge. And when we start talking about charge, you'll know more what I'm talking about. They have a negative charge or polarity, and in the middle are protons, which have a positive charge or polarity. So maybe as we start talking about charge, kind of think about magnets and the polarity of magnets. Polarity in electricity, we're talking about the polarity being positive or negative. When you talk about the poles or the polarity of magnets, you're talking about north and south. But it's the same law of physics that control all the things in this world as far as we know. And a lot of these analogies can lap over. So when you think about having magnets and holding them together, north and south or south and south, what that feels like are the forces. Although you can't see them, you can feel their presence, those forces that are being created from these different polarities, opposition of those forces or attraction of those. So the electrons are negative, the protons are positive. The electrons come off of the atom pretty easily compared to the protons that takes the nuclear reaction to do. We're not going to be doing that in our labs, but the electrons we can get to come off. But note that there's just as many electrons as there are protons. So the overall charge of an atom is 0 because every electron cancels out the positive charge of the proton. But if you lose electron, you tell me, if an atom is neutrally charged and I lose an electron, I make one come off the orbit, now what charge does the atom have?
A positive charge.
Positive charge. Everybody get that, right? If it's
Yep.
neutral, I lose it a negative. Now I have more positives than negative. The atom has a positive charge. If I were to gain an electron, then the atom would be negatively charged. And whenever you gain or lose electrons from an atom and it becomes charged, either positive or negative, it's said to be an ion. So an ion is a charged atom, either positive or negative. So ionization is usually stripping electrons off the atoms, but sometimes it's adding them to it. Electricity, they say here, is the flow of free electrons, but I'm going to say that that's really not electricity, that's current. Electrical current is the flow of free electrons. So you can see that the positive terminal in the battery, because it's positive, it's going to try to attract these negative electrons, and it'll come around to here, but now there's one extra in here, so it gets pushed out the other side. So these electrons go from atom to atom to atom to atom in the conductor. None of them go away, none of them leak out. There's always the same amount of electrons in this whole circuit from the beginning. It's just that we've got them moving as they're pulling off of one atom and getting replaced on the other end. So here they're showing a conductor, a semiconductor, and an insulator. You know, a conductor is something that allows current to flow easily. It's because of the structure. They have the outer orbit of an electron called the valence orbit. Atoms like to have 8. That's when they're saturated. If they only have a few electrons in the outer orbit, that tends to make them give it up easily. So that tends to facilitate or encourage electron flow and current. So those would be metals typically. If they're not very good at all, because they tend to have they're pretty full on the valence shell, then they don't give up those electrons easily. It's hard to shake them loose. So those are insulators, and glass and porcelain, wood, things like that. Somewhere in the middle, it's a semiconductor. It's halfway between a conductor and an insulator. We'll talk more about semiconductors when we get to that part. But think now just about conductors that tend to allow current to flow and insulators that do not. But understand that that's a spectrum, and all insulators can pass electricity if there's enough force to move those electrons. And all conductors still have a certain opposition to flow. They're not perfectly allowing things to get through it. So just keep that in the back of your mind. So this is showing ionization. And once you have, if you have a couple atoms here that are electrically neutral, and then you lose an electron, the other one gets, now you've got one that's negatively charged and you got another atom that's positively charged. Guess what? That attraction, that electrical force is going to pull them together just as if they were north and south magnets. Continuity. You've got to have a closed circuit so that those electrons can flow around in a continuous path. So the continuity comes from the same word as continuous, because if you have something that's open, if this circuit were to open up and the currents couldn't get from here to here, you have to have current flowing through your load for your load to work. So here's your source, here's your load, and you've got your conductors that gets the power from your source to your load. But you've got to have a complete path, because the electron leaves here, goes through, and it has to come back around and keep that continuous flow going. What we're doing here is we're making sure that this piece of conductor is continuous. How do we know? Well, if we have a battery and we have a bulb and we have electrons leaving here and they're trying to get back to here, and it gets to here and it can't get to here, we know that something in here is broken, or else the current would go from here to here. So this is the way we check to make sure that this is a continuous path. Continuity checker. In this example, you can see they took this lead off, put it up on the insulation because the insulator doesn't let current flow from the conductor out so that you don't get shocked when you pick up wires. This is showing a break in continuity. This would be an open circuit, and it causes the light to go out, causes the circuit to stop working. Most faults, I said, are either short circuit or open circuit. The majority of those two are open circuits. You know, like I say, a wire comes off, a cable gets worn and breaks a wire. That happens more often than short circuits. And another animation showing switch. A switch is purposefully designed to break continuity, because if you had the current flowing all the time, your load would be on all the time. You want to turn off a light or a motor or a fan, then you've got to break that flow, and that's what we're seeing here. In this little switch, you can actually see the schematic symbol for a switch activating and making and breaking continuity in the circuit. Again, if you want to look at these videos on your own time, if you just go to view them from that link, they're just going to be static. You're not going to be able to see them. You're going to have to download them and let PowerPoint play them to see these animations. So if you want, they're there for you. Another diagram, the continuity checker. Here I'm looking at same kind of configuration where I've got a battery inside this thing. I know you probably can't see my fingers on the screen. There's a battery inside of here. It's trying to push electrons through here, and if it can actually get through it, then the light will come on. And if not, I know there's a break in this wire. So static electricity. So you guys saw that little simulation. You can take a look at that. Probably, this is probably here to remind me to kind of talk about that a little bit. Let's just talk about this a little bit. What's happening here is when the foot drags across the carpet, in this case, it's ripping electrons off the atoms in the carpet. And as that happens, these John Travolta to voltage atoms are getting more and more negatively charged. So this figure is being more and more charged. It's charging up as it accumulates electrons. It's charging up negative. So it's more negative than the door that's neutral. And because of that, there's that tension. Just like if I had a bunch of magnets in one place and a bunch of magnets in another place that are opposite polarity, that tension wants to move things. That force wants to move things. In this case, the force is building up, wants to move these electrons, but it can't because there's not enough force to move through the air. There's too much opposition. Now, if I made that closer, then I can. Or if I got enough of a charge, if the difference builds up that's great enough that that force will overcome that, can you guys hear the sounds too?
Slightly.
Okay. So again, if you guys want to play with that, like I say, you paid good money for the course. And this is showing that how like charges repel, opposites attract. This is showing DC. It's called direct. It's for direct current. The direct actually means directional. It travels in one direction. They're showing a battery. That's a good example of a DC voltage source. And they're also showing the schematic symbol for a DC source. So become familiar with that. The waveform shows you that if you start a stopwatch and look at the direction and the level of the current, you see that over time it stays the same. It stays the same. It doesn't change direction. And in this case, it doesn't change level. Of course, as the battery discharges, you would see this start to drop down. Alternating current does change direction, and the outlet's a good example of that. And you can see the symbol here for alternating current. Alternating current does change direction. It rises in voltage and its level of intensity, it starts to drop off, and then for just an instant, it actually stops as it has to reverse directions and then travel the other direction. We'll talk more about these things too. Again, this is kind of just an introductory chapter, just to get you started. Different ways to create electricity. Either you're talking about voltage, that force, because you got a difference in charge, that force is voltage. And we can create that by moving electrons. I move electrons from one place to another, and now I have more electrons in one place than another, then that other place is negative compared to where they came from, which is now positive because it lost electrons. That creates the voltage, that difference in charge. And we can move electrons in different ways, and one is with light. Some substances are so sensitive to light that when light particles hit it, photons hit it, that will discharge electrons and get them to move. So I can get current happening or create a voltage by moving electrons from one place to another with light. Or I can use chemical reactions because of the way certain chemicals and elements work. It's still a matter of moving electrons from one place to another and ending up with more in one place than the other. When we talk about different elements, you're going to see that they have characteristics. They have characteristics of resistance, how much resistance they offer to electrical flow they have, and they call them coefficients. There's coefficients of, so that was a coefficient of resistivity. They have a coefficient of expansion, and what that means is that some metals, you heat them up 1 degree and they move 1 centimeter. You take a different metal and you heat it up the same amount, it expands more or less. So different elements have these different coefficients or properties. And if I take two metals that are dissimilar, like in this case here, this is a thermocouple. So a thermocouple, and you've got them in furnaces and things like that, heaters. They're two different metals, and when I heat them, one of them will dislodges electrons in one of them more than the other. So because of that, I have more electrons on one side of these than what's happening over here, and that difference is a difference of charge that creates a voltage. So I can make electrons move with heat, I can make them move with chemicals, I can make them move with light. The easiest way to make them move is with electric force. This voltage and the current that it can force through something is enough to hold open a relay. So when you hit your pilot light on, when you're trying to light something that's got the pilot light, and you have to hold that thing down for a little while. The reason you have to hold it down is for the flame, your pilot light flame, to get enough electrons to move so that there's enough voltage and current to hold open that little pilot relay that keeps that little pilot gas valve open. So you're holding that valve open manually, but there's a little coil there that will create a magnetic force that will hold that valve open, but first you've got to get enough electrons moving to do that. You can use some substances, they're using crystals here. This is a piezo effect. I guess a good example of that, if you have like a Weber grill or something where you have to push the little igniter and it just kind of clicks, that's probably a piezo cell that the pressure is causing electrons in that crystal to move. There's enough force there, it'll actually create a little arc. You know, we're talking about arcs shooting through the air. Real good examples of spark plug too. Use magnets. You can move electrons with magnets, and that's the underlying principle of generators. Whether it's the alternator in your car or whether it's the generators in the power plant, we're using magnets to move electrons. And once we move electrons, we can create voltages and we can create current. We'll learn more about motors and generators in this class too.